Okay, I think everything's working now. So the last thing we went over was epoxides, and I gave you the acid and base catalyst. And the way we remember that is acids are a pain in the ass. They go 3, 1, 2. And bases are basic bitches, so they go 1, 2, 3. Any questions, comments, or concerns about what we covered previously? No? Cool. Okay. So now we are going to go back. We already did those. Wow, we got further than I thought. So we're just going to go right into epoxides. So before I go ahead and draw these for you, what is a peroxy acid? Just anything you know about peroxy acids, please. And then as always, you can either unmute or talk in the chat. And if you have no idea what it is, that's also fine. You react alkenes to produce epoxides. Wow, I love not being able to speak English. So you're absolutely correct. The thing I want you to remember is that there are 3 oxygens. So O3 equals epoxide. That's just a little side note to remember. So essentially what it's going to look like is almost like a carboxylic acid, except we have an extra oxygen in there. And we can have any R group coming off of it. Specifically, if we have this long, complicated, ugly-looking one, we see that it has an O3, so it's going to have the same general structure over here. And then off of that, we see C6H5. So what functional group is C6H5? Yes, everyone's correct. It is a benzene ring. So let's draw that out. That was really ugly, but it's good enough. So coming off of the benzene ring, we have a chlorine, and it is M chlorine. Does anyone know what the M stands for? We haven't covered it yet, so if you don't know, that's okay. Methyl is a really great guess, but usually for methyl, but that's a really good guess. Someone said meta, exactly. So all meta means is that on the ring, it will be, Tiffany, since you knew that, how many carbons away do you think meta will be? If you don't know, that's okay. So close. You said 3 carbons. We're going to go over this in the next chapter, so I'll give you a quick little thing. So if we have a group here, let's say it's just an R group. Right here will be our ortho. Here will be meta. And this will be para. Again, we're going to learn about this in chapter 14. I'm very impressed that you even knew it, so awesome job. So meta in this case will be 1, 2 carbons away. So it will look like so. Any questions? Again, this is just in case he shows you a picture and he asks what it is, or he says which of the following are like a peroxy acid. You don't have to know all of the possible peroxy acids. Just kind of know how they're drawn. And you also have to remember that O3 means we're going to form an epoxide. Someone already said before that you react an alkene. So let's draw out an alkene. And you're going to react it with a peroxide. It doesn't matter which one you use. So let's just say just a generic CH3, CO3H. So the R group was just replaced with a methyl. And all you're going to do is take the alkene and essentially redraw it, right? Except now, since the double bond is trans, we know that our two substituents must be trans. And we're going to draw it pointing down for now, but we will do the stereochemistry in a second. And the reason we do it that way is because we want the epoxide on the plane, because that's the most stable option we have. So now it doesn't matter which side is wedge and which side is dashed. We know that it has to be trans to one another. So we're going to draw it like that. And this looks kind of ugly, so there we go. Ta-da! You don't need to know any kind of mechanism or anything. If you just understand this concept, you are golden. Any questions?
You said the oxygen has to be in the plane because it's stable that way?
Because it's just more stable. So our epoxides are really small rings, so they're really unstable. So if you have it like all up in different planes doing weird things, it's going to be unhappy. But here, if you draw it on the plane, it becomes really easy to visualize, and it's just happier that way.
Okay, thank you.
You're welcome. Okay, cool. So that's literally it. So if I were to ask you, what are the two methods for making epoxides, what would you guys tell me? Okay, someone gave me like a correct answer, but I want more specifically the reaction that we learned about. What is it called? We talked about it yesterday or Monday or whenever that was. Intramolecular Williamson ether synthesis, awesome. Or epoxy acid and an alkene. Perfect. So I'm going to write over here just a little summary, and I'll zoom back out, but for now. So for making oxides, we can either do intramolecular Williamson ether. I'm just going to write WE because I don't want to write Williamson ether. Synthesis. And alkene plus peroxy acid. Ta-da! And then it says it right here, so I won't rewrite it, but we can break epoxides in acid and base because they're super, super unstable. What about a regular old ether, like either cyclic or linear? Can we break it in both acid and base? Only acid, cool, and that's because in comparison, it's much more stable. Awesome, so that was kind of a boring start to the session, but epoxides are kind of boring. Any questions on anything we did so far?
Yeah, I'm sorry. What is WE synthesis again? I'm sorry. I didn't hear that part.
Okay, so let me show you while I explain. So we have our intermolecular Williamson ether synthesis, which just creates our linear ethers. And then the intramolecular Williamson ether, which creates cyclic ethers. One of our possible options is the epoxide. So the two ways that you can form an epoxide are the intramolecular Williamson ether or an alkene with a peroxy acid.
Okay, thank you.
You're welcome. Okay. So now is the fun part, my favorite part, the part that I like a lot. So I'm actually going to give you guys like a few minutes, I don't know how many, And I,
Scroll up a bit, please.
yeah. Here.
Okay, good. Thank you.
Okay, so I'm going to go ahead and create breakout rooms. And I'm going to put you guys in those rooms, and I'm going to give you like 5 minutes, and I'm going to project this. I don't know if it'll show up when you go into your sessions, so take a screenshot or write them down or whatever. I think there are 5 rooms, so I'm actually going to change that. Wait, hold on. 4 rooms, okay. Perfect. So there are 4 rooms. So group 1 will do the first one. Group 2 will do the second. 3. So let's go through this. Somebody from team 1, please unmute and help me answer this.
Okay. So what we thought, the only thing I'm a little confused about is the stereochem.
Okay.
But we added, I think I literally just did this one with you.
Yes.
So, do you want me to give you the name of what we got, like the structure, so it'll be easier?
I want you to just help me walk through. So what was the first step? What did you guys need to do?
So first we realized that this was an acid catalyzed cleavage, something like that. And then, so because of that, we know the order is 3-1-2. So we chose to break the tertiary bond between the oxygen and the tertiary carbon.
Cool. So
And then,
all right. Go ahead, sorry.
no, it's okay. And then I numbered it like you did to kind of like keep track of everything. So I numbered it 1, 2, 3, 4.
Okay, cool. I'll go ahead and do that for you. So what was in red, just so everyone knows, I wrote like what each carbon is. And then in blue, I'll write 1, 2, 3, 4. Cool. So one more thing I want you to tell me, what was the nucleophile in this case?
It was CH3O minus.
Cool. Okay, so I'll write that out. But you're absolutely right, that is the nucleophile. But what is more specifically, where are the electrons that are going to attack coming from?
The oxygen.
The oxygen. So in case we ask you about the nucleophile, the most technical specific answer is the oxygen. But awesome. So where are we going to add the nucleophile?
To the tertiary side.
Perfect. And you said stereochemistry was the thing you needed help with, right?
Yeah, I was confused when you added it. I know SN2 is a version of stereochemistry, but I was just a little confused in this case, since like the methyl was already wedged.
Okay, great. So I'm really glad you thought about it and you got to that point. So one thing that I want to mention first is, did we touch this stereocenter at all?
No.
No, exactly. So this is going to stay dashed, and that's going to become a hydrogen, right? It's going to get protonated. So when we do an SN2 and we attack, we have to attack opposite of the leaving group, right? So what will happen is the methyl will get flipped or pushed into the wedged position. So that will be our methyl. And then our nucleophile will add dashed. And it will be OCH3. And the nucleophile would just form because, well, this in itself can work as a nucleophile already, but this oxygen in the epoxide will take the hydrogen and become activated, and then the negative charge will allow it to be a better nucleophile. But yeah, you guys did amazing for this one. Thank you so much. Usually I would
Question.
everyone clap, but
I have a question.
yes, go for it.
Will the OCH3 and the OH always be trans to each other?
Like, you mean stereochemistry wise?
Yeah.
I'm sure there are exceptions, but for the purposes of this class, yes, they are going to be trans.
Okay, because when I'm doing like the Wiley, the answer, I always look for like them being trans. So I didn't know if that was like accurate or not.
Yeah, because
Okay.
you are like doing a backside attack, so they would have to be opposite in like a majority of cases. Great point. Thank you for that. And someone said, does the oxygen react with the acidic hydrogen or the methanol hydrogen? So in reality, like in an actual flask, if you did this reaction, it would probably react with the acid catalyst. So the reaction would look kind of different. But for our purposes, simplicity purposes, usually chemists will draw it taking this hydrogen, the methanol hydrogen, just because it allows us to draw in less steps. And I can show you what I mean by that in the next example. So team number 2, who's going to be my lovely assistant? Someone volunteered someone else, which I'm living for.
All right, I'll go.
Okay, cool. Thank you.
I feel like I did it wrong the first time, and then I did it again.
Okay.
So I kind of got confused where to break, because I know you break at the tertiary, but like, I don't know if you break like the left, like where the O is, or like the right.
That is a great point. So, for clarification, what would this carbon be? Primary, secondary, or tertiary?
Tertiary.
Cool. And then the other one is?
Primary.
Primary. Awesome, awesome. So the first thing I want to show is the activation step really quick. So this is going to take the hydrogen from here, give the electrons back, and we're going to form, let's see if it'll be nice to me. Haha. All right, and our nucleophile is now the same exact thing as before. I'm just drawing it flipped because it's easier. So you said we're going to attack the tertiary side, right? And why did you choose tertiary?
Because it's an acid catalyzed reaction.
Perfect. So we're going to attack this carbon because it's tertiary. And you said you were stuck on which bond to break, right?
Yeah.
Wait, can you guys still see what I'm writing? No.
Yeah.
Oh, you can't?
It's just left.
Okay. So sorry. Let's try to make it do its job. Although I do have to admit, this works a lot better, technologically speaking, than it was working on Monday. So I'm happy about that. Let me know once it pops back up for you guys and you can see me using my pointer. Maybe, possibly. Oh, I saw something happen. Not yet. Okay, let's give her a second. Of course, I said something nice and it decided, of course we're gonna be mean. That makes sense. Could you stop? Okay, thank you. And yes, I'm talking to my iPad, just mind your business. Give her positive affirmation. You're so right. You got this. You got this, iPad. Come on, WebEx. You're a queen. You can do this. It's preparing to share. Period, queen, you tell. Okay, in the meantime, how's everyone doing on this fine Wednesday? Hopefully better than... Haha! Okay. Whoever said positive affirmations, you were totally correct. That's all we needed. So it'll attack the tertiary side. And you're always going to break the bond that's attached to the oxygen. So in this case, it would have to be this bond right here that I'm highlighting, because we're not going to break a carbon-carbon bond. We're only going to break carbon-oxygen bonds. So that would mean it opens up that away. So let me zoom out a little bit. If we draw this again, and I'm lazy, so I'm just going to duplicate it. Does stereochemistry matter this time? No, because I gave you flat stuff to deal with. So 1 carbon away will become our OH, and then whoever was my volunteer, tell me what is added to the tertiary carbon. Like, what group is that going to be?
To the tertiary carbon.
Sorry, someone walked in and scared me. But yes, it's going to be OCH3. Yay, cool. I have a feeling it's not sharing again. This is depressing, huh? You guys are doing so great. Oh, it worked. Haha. All right.
I have a question. Why did it break there and not like the other place?
So, can you just clarify? Do you mean this one that I'm highlighting, or this?
No, like the blue, where you like showed where it was gonna break.
Okay, so it would break this way because we have an acid catalyst right here, and so that chooses tertiary over primary. And if we look here, this side is tertiary, this side is primary. So we're going to attack tertiary and kick open the epoxide towards the primary side. That's why we would have to break this bond. Sort of kind of makes sense?
Kind of. Like, why wouldn't the ring open?
Like the cyclohexane ring?
Yeah.
Because we're not going to break any carbon-carbon bonds. We're only going to deal with the oxygen. And since that carbon on the cyclohexane is going to start with 4 bonds and end with 4 bonds, you're totally not going to touch it at all. It might not be the best explanation, but for the purposes of this class, you don't have to know all the mechanics behind it. Just know that you're not going to break any carbon-carbon bonds, only bonds between a carbon and a heteroatom. So nitrogen, oxygen, sulfur. Does that kind of make more sense?
Yeah, thank you.
Okay, you're welcome. And then someone else had a question, I think. It just like screamed my laptop.
It was as hers. Yeah.
Yay. I love when you guys ask questions because I know that there's a bunch of other people who have the same question. So you guys are appreciated. All right, team 3.
Sorry.
Yes.
I'm sorry. Yeah, why did you pick the OCH3 to be that bond but not that bond? Could you, let me rephrase that. I'm sorry. Could you switch the OCH3 and the OH with the CH2 on the cyclohexane?
So, no. If I understood your question right, no. Because that's what he's going to try to trick you with. He'll give you like this, and he'll ask an acid or a base. So in an acid catalyst, the nucleophile will always attack the tertiary side. If you had a base catalyst, then it would prefer the primary side. So you would add it the opposite way. So I'll give you the same question with a base. So let's say OH minus. This would be your product. Does that answer your question?
Yes.
Okay, cool. anyone from group 3? Don't be scared. I know this was a hard one. That was the point. Oh, I forgot. Round of applause for my lovely assistant for number 2. You were amazing.
Oh, can you hear me?
Yes.
I think if group 3 doesn't do it, could I just do it?
Yeah, sure. That's fine.
So, first you got to look like, is it going to attack primary or tertiary? And then the oxygen on the CH3 is going to attack there's going to be a breaking on the tertiary. So it's going to attack the tertiary.
Sweet.
This is an acid.
Sorry, let me interrupt you for 1 second. You're absolutely right, and I love the way you thought about it. So the first step that you said was identify that it's an acid, so it will attack the tertiary side. Perfect. And then I love how you said that the nucleophile will specifically be the oxygen. 100% correct. And you also said that we're going to break this tertiary bond. So again, 100% correct. Awesome explanation.
And since there's like stereochemistry, it's going to be wedged on the OCH, the one that you're attacking.
Yes.
And the other part's going to kind of like drop down. I don't know. I can't explain it, but I'd have to draw it.
Yeah, I know what you mean. So we're going to attack from the
karate chopped or something.
So here's a tip that makes it kind of easier in the future. So anytime you're attacking, you have to flip the stereochemistry of the carbon. So if your epoxide is wedged, your nucleophile will have to be dashed. If your epoxide is dashed, it will have to be wedged. So you were totally right.
And the one that's not being attacked just stays the same.
Yes, and the one that's not being attacked will stay exactly the same. And before anyone says it, yes, if you're not wondering this, and if what I say confuses you, completely ignore it. But I always get someone ask about the stereochemistry of this carbon. Yes, technically it should be wedged here and look like that. You're correct. But I do it this way to show you a specific point. So don't freak out about the stereochemistry of this bond right here.
Someone drew like that, and I was like, "What?"
Yeah, so technically it would look like this, but that is the ugliest thing I've ever seen. So I'm not going to do that to you.
Yeah, that way looks better.
Yeah, I think so too. And then someone said they thought OCH3 would be dashed because it was already wedged. So if I'm understanding your question, so yes, the epoxide was already wedged, so the OCH3 would have to be dashed. And then
that was before you said that. She said.
Oh, okay. Sorry, my bad. Thank you. Okay, and group number 4, I'm so sorry. I know one of your lovely volunteers was going to help me, but since we're running out of time, I want to just give you guys the answer really quick. But thank you to the group 3 volunteer. Okay, so real quick, you guys kind of should be able to tell that these are almost exactly the same thing. The only difference is that now we're using a base catalyst. And so someone tell me, what is the order for a base?
1, yeah.
1, 2, 3, perfect. And because why?
I'm sorry. Doesn't the Na make it negative, which makes it an acid?
No.
Oh, did I get that reverse? I think I got that reverse.
So anything with a negative charge is going to be a what or a what, everybody?
A base, my bad.
A base or a nucleophile. Awesome, awesome. So yeah, I mix up acids and bases all the time. If you don't think about it, sometimes it's easy to mix up. So very valid question.
I know.
So between this, we're actually going to now pick the opposite side of what we've been attacking before. So the oxygen will attack primary. So now we're going to break this primary bond and open towards tertiary. And what I said about stereochemistry is still valid. So the side that becomes attacked or the nucleophile will be added opposite to whatever the epoxide already was. So don't forget this extra carbon here. And coming off that carbon, we're going to be wedged. And we have an OCH3 added. And then coming off of the tertiary carbon, we will have a dashed OH. I'll now zoom out in case anyone wants to take a picture or has any questions or anything. Oh,
Why was this?
Go
sorry.
Go ahead.
Why was this a base catalyzation?
So the reason it was a base is because the catalyst on the bottom my bad. The catalyst on the bottom was supposed to just say H-. I think there was an error when I uploaded it, or maybe I just did something stupid. Thank you for pointing that out. That was just supposed to say H-.
Oh, so we're looking at the bottom, not like the top.
Yeah.
Okay.
Also, thank you for reminding me there is a sign. So I'm going to sign in. Please sign in. It would be easier if it will let me paste something. That would be cool, but I think Don't you love when you copy something and then it pastes something completely different? That's cool.
Love it.
Because I literally copied the link to a Google Doc, and then when I pasted it said tumblr.com, and I was like, I don't know what that is, but that's frightening. So, and then someone said, did I say H+ or H- for the catalyst? No, it could give you an actual base or an actual acid, but the reason I replaced it to H+ and H- is because he usually gives it to you that way. So it's easy if you guys know that H+ is acid, H- is base. But he could have also given you any other base, so like NaOH, KOH, anything else. That's just the most common one. And I think what I meant to write on the number 4 arrow was CH3OH, CH3ONA, because that's how it'll show up on your exams, not the other way around. And so all that is telling us is that our catalyst has a negative charge, so it's a base, and essentially the conjugate base of our alcohol. So if that didn't make any sense to you, that's completely fine. Just if you know it the way I did it the first time, that's good enough. But those are just other ways that you can write it out. And then, so why did number 2 oxygen attack the other? Okay, so someone asked why in number 2 we activated it first. Just because someone asked about the activation step, so I showed it to you. It happens technically first in all of these. I just didn't bother to draw it out because you don't have to draw out every single step. You just have to know the final product, if that makes sense. So that's pretty much all I have for you guys today. I hope you have a great day. If you have any questions, I'll stay on for another minute or so. But you guys did amazing.
So are these oxide reactions? Or
yeah,
no?
So this is cleavage of epoxides.
Okay, so next time are we doing epoxide reactions?
Well, yes, this is what I meant by epoxide reactions. Yes.
Okay.
Another way to say it would just be cleavage of epoxides.
So these are all the reactions we need to know for chapter 11?
Yep, pretty much. Before I say definitely yes. Yep, that's it.
We didn't get into the I don't know how to say it, but it starts with a G.
Yeah.
Yes.
Grignard is actually chapter 12, and we'll go over it Friday.
Okay, thank you. I'm just having a hard time like following along his videos, and it's just really confusing. His videos and the summaries, it's just like all over the place.
Yeah,
So I don't know what I should be on right now.
I'm actually really glad you said that. I forgot to mention this, so I'll mention it Friday. I know the videos on this are really, really confusing because when he filmed those like a million years ago, he taught this in a different order. So he completely mixed together chapter 11 and 12. So in the videos, chapter 11 and 12 are like all mushed together. But the last semester or two, he decided to do them separately. So do chapter 11 first and then chapter 12. So that's why the handouts don't really match with his chapter the chapter summaries and the handouts don't match his lectures because he does it in a different order now. That being said, it's really frustrating, and I would just focus on the summary, the order that the summary goes in when you watch the videos, and kind of just orient yourself as you go.
Okay, and I know there was some chapter 11 stuff on the first test. Will that come in the second test as well?
So as far as I know, no. So the second exam will start here. Nope, here. At ethers.
Okay, thank you so much.
You're very welcome. That being said, though, I have to double check with him, but I believe oxidation will come back and review with reduction. So I don't know if he's going to give you specifically oxidation questions, but we're going to cover it, and he covers it again in lecture.
Yeah, because in the exam, I had no oxidation in there, so I wasn't really sure if that was going to also be an exam too.
Yeah, that's what, because he hasn't gotten back to me yet, but what I figure is that it will be asked on exam 2, even though it was listed under exam 1. But before I say anything for certain to you guys, I want to double check with him.
Okay, thank you.
You're welcome. And then someone said, would the cleavage of a tertiary carbon be an SN1? So for the purposes of this, it's always going to be SN2, even though that kind of counteracts or contradicts, I should say, what you guys were taught in Orgo 1. But as far as these epoxide reactions go, it's always going to be SN2 for cleavage. Yeah, so just for the cleavage, it'll be SN2.
Are you going to post the SI handout for this chapter?
So this one was the same handout as the last exam.
Chapter. Okay.
I will today post the rest of the handouts, and I'll send you guys an email because I'm not sure if my stuff is posting properly.
Okay, cool. Thank you.
You're welcome. And then for the cleavage of normal ethers, yes, I believe it's the same rule. I don't think there's exceptions, but I can look into it because I'm not 100% certain. And then someone said, quick question. Yes, Danielle, what's up? Or Daniel. Danielle, I think. What's your question? So for Williamson ether, yes. Does it involve epoxides? So yes, intermolecular will not make an epoxide. It will just make a linear ether. But the intramolecular will make cyclic ethers. So one of the options is an epoxide. You're welcome. Have an awesome day, everyone.